And so if you solve for t, you get half of mg by 2. This is half of what we had earlier, right? So what the moral of the story is that if you add more ropes, you distribute the force that you have to apply, which again makes sense. If you have two people pulling against one person, then the two people will have to pull less than that one person who's doing all the work. Alright. Okay, good. All of that makes sense. Let's move on to level 2. Level 2 is this hangman-like kind of looking thing, so we can do what we always do. So there's always going to be an MG. We know that for sure right off the bat. MG, directed downwards. And since there's two strings, there's going to be a T1 and a T2. So a force of tension along each string, because they're both gonna apply a force of tension, right? It's just figuring out what that tension is, especially in terms of mg, which is what we know. So T1, since it's at a diagonal, we can split it up into components, which you should know is, so the y component is going to be T1 sine theta, since it's opposite to the theta, and the x component is T1 cosine theta, which is adjacent to the theta. Now theta, we're assuming you're given like the angle from the top kind of thing, and if you just do like a let's get a pointer, let's get fancy. So if you think about geometry, this is a parallel line, and this is a parallel line, and if you have a transversal, if you're given this theta is going to equal this theta. So we're assuming this is what you're given. Okay, so you have that now, and T2, you can't really split it up into any components. So we know this is a static system, it's not moving anywhere, so we can do like a component by component analysis. So let's start with the x direction. In the x direction, f net equals 0, of course, because it's not moving sideways, it's not moving right to left. T2, here, this T2 has to equal T1 cosine theta, because these are the only two forces acting in the x direction, and they're acting opposite to each other, and since it's not moving, they have to have the same force applied, like a tug of war. Let's think about the tug of war in the y direction. There's a T1 sine theta, and an mg, where we only have these two in the y direction, so f net equals 0, so mg has to equal T1 sine theta, and now you can solve for T1 by dividing mg by sine theta if you just do some nice little algebra here. Alright, moving on. This is also a level 2, according to me. Now we have two tensions applied, and this, if you're given this, it's theta 1, theta 2, and wow, I really didn't do this well. Okay, let's theta 1, theta 2. We're gonna split them, okay, never mind. We're gonna add mg first, as we always do, and then we're gonna add the T1 and the T2, as we always do. Since they're at diagonals, we can split them up into components, because physicists like to do that. And since we're given theta 1, we have to make sure this is T1 sine theta 1, and since it's theta 2, T2 sine theta 2, and okay, so in the x direction, we have T1 cosine theta and T2 cosine theta. So f net equals 0 since it's not moving right to left, and T1 cosine theta has to equal T2 cosine theta. Now this is a lot of variables, so actually you'd probably have a system of equations at hand. Let's continue though. So in the y direction you have both T1 sine theta 1 and T2 sine theta 2 acting against mg. And so in the y direction, you have to add those two together, so this one, and then set that equal to mg. And so now you can use these two to solve a system of equations however you want to, and that just takes basic math skills.